Well, last time we talked about compound data, and there were two main points to that business. First of all, there was a methodology of data abstraction, and the point of that was that you could isolate the way that data objects are used from the way that they're represented. This idea that there's this guy George, and you go out and make a contract with him, and it's his business to represent the data objects, and at the moment you're using them, you don't think about George's problem. And then secondly, there was this particular way that Lisp has of gluing together things to form objects called pairs, and that's done with const, car, and cdr, and the way that const, car, and cdr are implemented is basically irrelevant. That's sort of George's problem of how to build those things. It could be done as primitives, it could be done using procedures in some weird way, but we're not going to worry about that. And it's an example. We looked at rational number arithmetic. We looked at vectors, and here's just a review of vectors. Here's an operation that takes the sum of two vectors. So we want to add this vector v1 and this vector v2, and we get the sum. And the sum is the vector whose coordinates are the sum of the coordinates of the pieces you're adding. So I can say, to define make vect, right, to add two vectors, I make a vector whose x-coordinate is the sum of the two x-coordinates and whose y-coordinate is the sum of the two y-coordinates. Okay, and then similarly, we could have an operation that scales vectors. So here's a procedure scale that multiplies a vector v by some number s. So here's v. V goes from there to there, and then I scale v. I get a vector in the same direction that's longer. And again, to scale a vector, I multiply the successive coordinates. So I make a vector whose x-coordinate is the scale factor times the x-coordinate, and whose y-coordinate is the scale factor times the y-coordinate. So those are two operations that are implemented using the representation of vectors, and the representation of vectors, for instance, is something that we could build in terms of pairs. So George has gone out and implemented for us make vector and x-coordinate and y-coordinate, and this could be done, for instance, using const, car, and cdr. And notice here I wrote this in a slightly different way. The procedures we've seen before, I said something like, say, make vector of x and y, const of x and y, and here I just wrote make vector const. And that means something slightly different. Previously we'd say, define make vector to be a procedure that takes two arguments x and y and does const of x and y. And here I'm saying, define make vector to be the thing that const is. And that means that's almost the same as the other way we've been writing things. And I just want you to get used to the idea that procedures can be objects and that you can name them. Okay, well, there's vector representation. And again, if that was all there was to it, this would all be pretty boring. And the point is, remember that you can use const to glue together not just numbers to form pairs, but to glue together arbitrary things. So for instance, if we'd like to represent a line segment, say the line segment that goes from a certain vector, say the segment from the vector 2, 3 to the point represented by the vector 5, 1. If we want to represent that line segment, then we can build that as a pair of pairs. So again, we can represent line segments. We can make a constructor that makes a segment using const, selects out the start of a segment, selects out the endpoint of a segment. And then if we actually look at that, if we peel away the abstraction layers and say, what's that really as a pair of pairs? We'd say, well, that's a pair. Here's the segment. Its car, right, its car pointer is a pair. And its cdr is also a pair. And then what the what the car is, here's the car, that itself is a pair of 2 and 3. And similarly, the coulter is a pair of 2 and 3. And let me remind you again that a lot of people have some idea that if I'd taken this arrow and somehow written it to point down, that would mean something else. That's irrelevant. Right? It's only how these are connected and not whether this arrow happens to go vertically or horizontally. And again, just to remind you, there was this notion of closure. See, closure was the thing that allowed us to start building up complexity, that didn't trap us in pairs. Particularly, what I mean is the things that we make, having combined things using consts to get a pair, those things themselves can be combined using consts to make more complicated things. Or as a mathematician might say, the set of data objects in Lisp is closed under the operation of forming pairs. And that's the thing that allows us to build complexity, and that seems obvious, but remember, a lot of the things in the computer languages that people use are not closed. So for example, forming arrays in BASIC and Fortran is not a closed operation because you can make an array of numbers or character strings or something, but you can't make an array of arrays. And when you look at means of combination, you should be asking yourself whether things are closed under that means of combination. Well, in any case, because we can form pairs of pairs, we can start using pairs to glue things together in all sorts of different ways. So for instance, if I'd like to glue together the 4 things 1, 2, 3, and 4, there are a lot of ways I can do it. I could, for example, like we did with that line segment, I could make a pair that had a 1 and a 2 and a 3 and a 4. Right? Or if I liked, I could do something like this. I could make a pair whose first thing is a pair, whose car is 1, and whose coulter is itself a pair that has the 2 and the 3, and then I could put the 4 up here. So you see there are a lot of different ways that I can start using pairs to glue things together, and so it'll be a good idea to establish some kind of conventions, right, that allow us to deal with this thing in some conventional way so we're not constantly making an ad hoc choice. And Lisp has a particular convention for representing a sequence of things as essentially a chain of pairs. And that's called a list. And what a list is essentially just a convention for representing a sequence. I would represent the sequence 1, 2, 3, and 4 by a sequence of pairs. I'd put 1 here, and then the coulter of this would point to another pair whose car was the next thing in the sequence, and the coulter would point to another pair whose car was the next thing in the sequence. So there's 3, and then another one. So for each item in this sequence, I'll get a pair. And now there are no more, so I put a special marker. That means there's nothing more in the list. Okay, so that's a conventional way to glue things together if you want to represent a sequence. Right? And what it is a bunch of pairs. The successive cars of each pair are the items that you want to glue together. And the coulter pointer points to the next pair. Now, if I actually wanted to construct that, what I would type into Lisp is this. I'd actually construct that as saying, well, this thing is the const of 1 onto the const of 2 onto the const of 3 onto the const of 4 onto, well, this thing nil. And what nil is a name for the end of list marker. It's a special name, which means this is the end of the list. Okay, so that's how I would actually construct that. Of course, it's a terrible drag to constantly have to write something like the const of 1 onto the const of 2 onto the const of 3 whenever you want to make these things. So Lisp has an operation that's called list. And list is just an abbreviation for this nest of consts. So I could construct that by saying that is the list of 1, 2, 3, and 4. And all this is another way, a piece of syntactic sugar, a more convenient way for writing that chain of consts. Const of const of const of const of const onto nil. So for example, I could build this thing and say, I'll define one to 4. I'll define 1 to 4 to be the list of 1, 2, 3, and 4. Okay, well, notice some of the consequences of using this convention. First of all, if I have this list, this 1, 2, 3, and 4, the car of the whole thing is the first element in the list. Right? How do I get 2? Well, 2 would be the car of the cdr of this thing 1 to 4. It'd be 2. Right? Right, I take this thing, I take the cdr of it, which is this much, and the car of that is 2. And then similarly, the car of the cdr of 1 to 4, cdr car, would give me 3, and so on. Let's take a look at that on the computer screen for a second. But I could come up to Lisp, and I could type define 1 to 4 to be the list of 1, 2, 3, and 4. And I'll tell that to Lisp, and it says fine, that's the definition of 1 to 4. And I could say, for instance, what's the car of the cdr of 1 to 4? Close paren, close paren. Right, so the car of the cdr would be 3. Right, or I could say, what's 1 to 4 itself? And you see what Lisp types out is 1, 2, 3, 4 enclosed in parentheses. And this notation, typing the elements of the list enclosed in parentheses, is Lisp's conventional way for printing back this chain of pairs that represents a sequence. So for example, if I said, what's the cdr of 1 to 4, that's going to be the rest of the list. That's the thing pointed to by the first pair, which is again a sequence that starts off with 2. Or for example, if I go off and say, what's the cdr of the cdr of 1 to 4, then that's 3, 4. Or if I say, what's the cdr of the cdr of the cdr of the cdr of 1 to 4, and I'm down there looking at the end of list pointer itself, and list prints that as just open paren, close paren. You can think of that as a list with nothing in there. All right, see at the end what I did there is I looked at the cdr of the cdr of the cdr of 1 to 4, and I'm just left with the end of list pointer itself, and that gets printed as open close. All right, well, that's a conventional way, as you can see, for working down a list by taking successive cooters of things. It's called cootering down a list. And of course, it's pretty much of a drag to type all those cooters by hand. You don't do that. You write procedures that do that. And in fact, one very, very common thing to do in Lisp is to write procedures that sort of take a list of things and do something to every element in the list and return you a list of the results. So what I mean, for example, is I might write a procedure called scale list. And scale list, I might say, I want to scale by 10 the entire list 1 to 4. And that would return for me the list 10, 20, 30, 40. Right, so it returns the list. And, well, you can see that there's going to be some kind of recursive strategy for doing that. How would I actually write that procedure? The idea would be, well, if you'd like to build up a list where you've multiplied every element by 10, what you say is, well, you imagine that you'd taken the rest of the list, right, the thing represented by the cooter of the list, and suppose I'd already built a list where each of these was multiplied by 10. That would be scale list of the cooter of the list. And then all I have to do is multiply the car of the list by 10, and then const that onto the rest, and I'll get a list. Right, and then similarly, to have scaled the cooter of the list, I'll scale the cooter of that, and const onto that 2 multiplied by 10. And finally, when I get all the way down to the end, and I only have this end of list pointer, right, this thing whose name is nil, well, I just return an end of list pointer. So there's a recursive strategy for doing that. Here's the actual procedure that does that. Right, this is an example of the general strategy of cootering down a list and so-called consting up the result. Right, so to scale a list L by some scale factor S, what do I do? Well, there's a test, and list has a predicate called null. Null means, is this thing the end of list pointer? Or another way to think of that is, are there any elements in this list? But in any case, if I'm looking at the end of list pointer, then I just return the end of list pointer. I just return nil. Otherwise, I const together the result of doing what I'm going to do to the first element in the list, namely taking the car of L and multiplying it by S. And I const that onto, recursively, scaling the rest of the list. Okay, so again, the general idea is that you recursively do something to the rest of the list, to the cooter of the list, and then you const that on to actually doing something to the first element of the list. When you get down to the end here, you return the end of list pointer. And that's a general pattern for doing something to a list. Well, of course, you should know by now that the very fact that there's a general pattern there means I shouldn't be writing this procedure at all. What I should do is write a procedure that's the general pattern itself, that says do something to everything in a list and define this thing in terms of that. Right? Make some higher order procedure. And here's the higher order procedure that does that. It's called map. And what map does is it takes a list L, and it takes a procedure P, and it returns the list of the elements gotten by applying P to each successive element in the list. Right, so P of E1, P of E2, P of En. Right, so I think of taking this list and transforming it by applying P to each element. And you see all this procedure is exactly the general strategy I said. Instead of multiply by 10, it's do the procedure. If the list is empty, return nil. Otherwise, apply P to the first element of the list. Right, apply P to car of L, and const that onto the result of applying P to everything in the footer of the list. So that's a general procedure called map, and I could define scale list in terms of map. Let me show you that first. But I could say scale list is, another way to define it is just map along the list by the procedure which takes an item and multiplies it by s. Right, so this is really the way I should think about scaling a list. Build that actual recursion into the general strategy, not to every particular procedure I write. And of course, one of the values of doing this is that you start to see commonality. Right, again, you're capturing general patterns of usage. So for instance, if I said map the square procedure down this list 1 to 4, then I'd end up with 1, 4, 9, and 16. Right, or if I said map down this list lambda of x plus x10, if I mapped that down 1 to 4, right, I'd get the list where everything had 10 added to it. Right, so I'd get 11, 12, 13, 14. Right. And you can see that's going to be a very, very common idea, doing something to every element in the list. One thing you might think about is writing map in an iterative style. The one I wrote happens to involve a recursive process, but we could just as easily have made one that involves an iterative process. But see, the interesting thing about it is that once you start thinking in terms of map, see, once you say scale is just map, you stop thinking about whether it's iterative or recursive, and you just say, well, there's this aggregate, there's this list. And what I do is transform every item in the list, and I stop thinking about the particular control structure and order. That's a very, very important idea. And it, I guess it really comes out of APL. It's sort of the really important idea in APL, that you stop thinking about control structures and you start thinking about operations on aggregates. And then about halfway through this course, we'll see, when we talk about something called stream processing, how that view of the world really comes into its glory. This is just a sort of cute idea, but we'll see much more applications of that later on. Oh, let me mention that there's something that's very similar to map that's also a useful idea, and that's, see, map says I take a list, I apply something to each item, and I return a list of the successive values. There's another thing I might do which is very, very similar, which is take a list and some action you want to do, and then do it to each item in the list in sequence. Don't make a list of the values, just do this particular action. And that's something that's very much like map. It's called for each, and for each takes a procedure and a list, and what it's going to do is do something to every item in the list. So basically what it does, it says if the list is not empty, right, if the list is not null, then what I do is I apply my procedure to the first item in the list, and then I do this thing to the rest of the list. I apply for each to the footer of the list. Right, so I do it to the first of the list, do it to the rest of the list, and of course, when I call it recursively, that's going to do it to the rest of the list, and so on. And finally, when I get done, I have to just do something to say I'm done, so we'll return the message done. So that's very, very similar to map. It's mostly different in what it returns. And so, for example, if I had some procedure that printed things on the screen, if I wanted to print everything in a list, I could say for each, print this list. Or if I had a list of figures and I wanted to draw them on the display, I could say for each, display on the screen this figure. Okay. Let's take questions.
It doesn't create a new copy with something done to it unless you explicitly tell it to do that. Is that correct?
Right. Yeah, that's right. For each does not create a list. It just sort of does something. So if you have a bunch of things you want to do, and you're not worried about values like printing something or drawing something on the screen or ringing the bell on the terminal or something, you can say for each. Do this for each of those things in the list. Whereas map actually builds you this new collection of values that you might want to use. It's just a subtle difference between them.
Could you write map using for each so that you did some sort of cons or something to build the list back up?
Well, sort of. I mean, I probably could. I can't think of how to do it right offhand. But yeah, I could arrange something. I think. Yeah.
There's a fundamental difference between map and for each. One is recursive and the other is not, in the sense you defined early yesterday, I believe.
Yeah, about map and for each and recursion. Yeah, that's a good point. For the map procedure I wrote, that happens to be a recursive process. And the reason for that is that when you've done this thing to the rest of the list, you're waiting for that value so that you can stick it on to the beginning of the list. Whereas for each doesn't really have any values to wait for. So that turns out to be an iterative process. That's not fundamental. I could have defined map so that it's evolved by an iterative process. I just didn't happen to.
If you were to call for each with a list that had embedded lists, I imagine it would work, right? It would give you the internal elements of each of those internal lists. Okay,
the question is if I call for each or map for that matter with a list that had lists in it, although we haven't really looked at that yet, would that work? And the answer would work. The answer is yes in the sense I mean work, and no in the sense that you mean work. Mm-hmm. Because all that, see, if I give you a list where hanging off here is something that's not a number, maybe another list, mm-hmm. or another const or something. For each just says do something to each item in this list, and it goes down successively looking at the critters. Okay. And as far as it's concerned, the first item in this list is whatever's hanging off here. Mm-hmm. That might or might not be the right thing.
So it wouldn't go down into the...
And it absolutely not. Mm-hmm. I could certainly write something else. There's another... What you're looking for is a common pattern of usage called tree recursion, where you take a list and you actually go all the way down to what's called the leaves of the tree. And you can write such a thing, but that's not for each, and it's not map. Remember, these things are really being very simple-minded. Okay, no more questions? All right, let's break.